I wanted to review again with you some of the stuff we did the other day on z-scores and on the normal distribution, the normal curve. Let's start out with a simple explanation of the z-scores. Again, I think that it's really a very simple computation. If you could do the standard deviation computation, the z-score is very simple after that. Let's draw a number line here, starting 1. Let's see, I'm going to end it at 7. So let's do 2, 3, 4, 5, 6, 7, and let me just fix my number line here so it looks like a number line. Alright, I'm going to have a set of scores, and the scores we're going to work with are going to be 2, 3, and 7. And we know that the mean of these scores is 4 because we have 2 plus 3 plus 7 equals 12. We have 3 scores, so the mean is going to be equal to 4. And I'll put a dot over there for that mean. Alright, let me get rid of that. The standard deviation for this group of scores, let me just write that mean down. Mean equals 4. Standard deviation is going to be equal to 2.2. You can figure that out yourself. I'm not going to bother doing the calculation right now. Alright, let's see how we would get those z-scores. We're going to do the z-score formula, again, is z equals the score we're testing minus the mean of the distribution over the standard deviation. So the mean of the score that we're testing, the score that we need the z-score for, minus the mean divided by the standard deviation. And just for clarity, I'm going to put some parentheses around that. Okay, so the first z-score is going to be 2 minus 4. And the second one is going to be 3 minus 4. And the third one will be 7 minus 4. That's our mean, divided by the standard deviation, excuse me, which is 2.2, divided by 2.2, divided by 2.2. If you do this little bit of arithmetic, you're going to get negative 0.9 for our first z-score, negative 0.5 for our second z-score, and positive 1.4 for our second z-score. So it's really as easy as that. It's just a question of subtract the mean from the raw score you're interested in, and divide the result of that subtraction by the standard deviation of all the scores. And you'll recall that all the time, no matter what, the mean of a z distribution is always equal to 0, and the standard deviation of a z distribution is always equal to what? To 1. I can show you here. It's very obvious that the mean has to be equal to the mean of the z distribution has to be equal to 0. These are my z-scores that I've just computed right over here. And you can see, remember the formula for a mean, not that you really need a formula, the sum of the x's divided by n. So the sum of these x's, the sum of these z-scores, which are our x's in this instance, are negative 0.9 plus negative 0.5, which is the same as saying negative 9 minus 0.5 is equal to negative 1.4, and we have positive 1.4 over here. So for the z distribution, it's a little bit harder to see this, why the standard deviation is always 1. There's a little bit more mathematics we have to do to show you that, and I'm going to hope that you'll be willing to accept what I'm saying here about that. Let's go on to just put this onto a number line so we can get used to that. I'm going to make this, put my mean in the middle. Mean is going to be equal to 0. And let's go out 3 standard deviations. Okay. Doesn't really matter how many we do, but let's do 3 just for the heck of it. So let me put, for our first z-score on the negative side, let's label this. That's -1, -2, -3 standard deviation units away from the mean. That's +1, +2, +3. All right, so our first one is -0.9. I've labeled that over there. The next one's a little bit easier. That's -0.5 over there. And our final one, the z-score for our raw score of 7, is 1.4. That's going to be about there. Okay. The important thing to remember, the key thing to remember with this, is that the relative positions of these scores have not changed. The scale has changed, but the distance, the relative distance of each score from the mean and each score from every other score is still the same.